So my roadmap for today is to have a look at basics of mortality, and then I will go into genetics, and genetics is split into the piglet side and to the sow side, and the sow side is the mothering ability kind of stuff. I will have one slide, I guess, on the genomics, and I'm scared of that because Max is in the room. And I'll end with a mission to us all to try to reduce this mortality. So what is the challenge? In the end, our business is to transfer feed to pork in the farrow finish, the business. It is about efficiency, and it is a challenge because feed prices are increasing and will be high. So we're looking at feed efficiency as pork over feed. But the system leaks. The system leaks actually quite a bit. We do lose quite a few animals in all the phases of the whole farrow to finish the business. So if you look at the losses, the best estimates of the ova shed, so eggs which can be fertilized, is around 30, a bit lower, I guess. Then we get some 15 piglets born if you do a good job. If you do a good job, you have some 15 piglets total born. You have one stillborn. You have around 14.3% pre-weaning mortality, 2% nursery, 3% to finishing. I guess that all of us think that this is an acceptable system. If I calculate from the total borns, then 76% of the total borns reaches the plant. The 30 ova to 15 piglets born is a loss already, and this could lead to crowding. It could be a cause already, that we put too many fetuses in the uterus, and with that damage the quality of the piglets, with later negative consequences for mortality and for production. There's a lot of very good work done in Canada at the University of Alberta. Then during the lactation or around lactation, the farrowing process, you lose one stillborn and 14.3. This amounts to exactly 3 piglets. That's why I took the example. So from 15 minus 3 is 12 animals the weaned. So this amounts to 20% perinatal mortality. I guess that is a bit lower than the industry average. It's a bit higher. In Europe we have the similar results. If you go to Brazil, then the levels are lower because of the 24 hours, the people in the barn helping out. And if you help out 24 hours a day, then you can reduce stillborns. Since quite a few piglets, which are considered stillborn, are actually live-born, but they die before you see them. So you can reduce stillborn. But on average, 20% worldwide is not too bad an estimate. What I will like you to learn later on is that if we select for this perinatal the mortality, it will influence the earlier phases. It will have consequences for the implantation of the piglets. It will help uniformity of the piglets, and with that it will help in the loss from these 30 eggs towards the 15 piglets. And that's what we did, the work which we did last year. There is a strong positive genetic correlation between strength of the piglets and longevity. So if we select for better surviving piglets, they will live longer. They're better bolted, more or less. They're stronger. This is a graph I took from Dutch results, and this is the hours spent per piglet in a farrowing unit, and that's easy calculation. It is total the piglets and total labor, and just divided. In 1997, it was 0.7 hours on average spent per piglet produced, and in 2007 it was 0.35. So half. In 10 years' time, we halved the amount of available labor. And if I would add, I tried to do that last night, but I didn't succeed. If I add the 2008 and 2009, it fits the curve very nicely. So as an industry, we spent less and less time in per piglet. So we need stronger sow the piglet entities. Basics. And here are two curves. The rightmost, or the low one, is the normal bell curve distribution for birth weight. Internationally, we tend to use kilograms. In this country, for some reason, you use pounds. So these arrows indicate the pounds. The left one is 1 pound, 2 pounds, 3 and 4 pounds. So the bell-shaped curve is normal distribution, standard deviation within little standard deviation is the 270 grams or something like that. And then that S-shaped curve is the survival curve. So if you take the 2-pound piglets, then livability of a 2-pound piglet on average is around 50%, 55%, something like that. And the livability of the 4-pound piglets is 92%. So we're producing more piglets and we want them to live. So what to do? Option 1 is to increase birth weight. So you could shift the birth weight, the distribution to the right. Then you have fewer small ones. Well, that makes sense. If you have fewer small ones, then your livability is better. A second possibility is to make them more uniform. And again, you get fewer small ones, but you do lose some of the very heavy ones. But the loss in survival of the very heavy ones is not as large as the gain on the low side. So it pays to reduce variation, to make them more uniform. That will benefit your survival. And then the third option is to increase livability, increase survival, to raise that survival curve. So the 2-pound, the piglets had 55% livability, and in this the slide it is, 65 or something, 63. So if we are able to raise that livability curve, that could pay quite a bit. Animals. There is the Pietraia, the sired animals, and there's Duroc sired animals. And first, if you look at the bell-shaped curves, then there's very little difference between the Pietraia and the Duroc. The distributions are highly the same. And that is what we find time and again. The influence of the service sire on birth weight is very low. Birth weight in pigs is a maternal trait. It is the size of the uterus. It's the blood flow which decides the weight of the piglets. It's not the service sire. So in that sense, the Pietraia and the Duroc have exactly the same distribution in birth weight. But if you look at the survival curve, there is a huge difference in survival. If you take the 1 kilogram pigs, then the Pietraia sired pigs have a livability of 60% in this situation, and the Duroc sired pigs have, 75%, a difference of 10 to 15%. Well, probably you recognize it. Durocs give stronger piglets. But if the differences are there between lines, they might be there within lines. So in this graph I took sires of one line and looked at offspring. And I'll explain that later. We have a quite large database. So each of these sires had at least 350 offspring. So the curve is estimated quite accurately. So if you look at this graph, and then all of these sires could be on the same stud. So if you take the lowest one, the 2-pound piglets, they live from one sire 40%, and from other sire they live 90%. That's a huge difference in livability. Well, it is easy which sire you would like to use for the production of piglets. So there is genetic variation between lines and within lines for livability of piglets. That is essentially already genetics. So how to exploit that in a genetic improvement program? First is, who are we going to blame? I took my PhD on genetics of the piglet survival, and when I started I was quite naive about questions like this. And the general idea was, if a piglet dies, it's a veterinarian problem. Well, if you have too much mortality, go to the vet and they will solve something. Only later we discovered that there was some genetics involved. And first is, first is to look at the sow, because the piglet is so small, he or she can't help if she dies. So the problem is the sow. Okay. So the classic approach to livability is to model litter mortality, litter mortality, as herd year season. In Brazil they have lower mortality than in the US and in Europe. So there are differences in climate, in labor and stuff like that. So after correction for all those effects, the herd year season effects, then if you look at the genetic differences, then the unit of interest was the sow. So you calculate that this sow has 6% mortality and another sow has 25% mortality and whatever, and then you run the heritabilities and your breeding values and you go for it. But what I've shown you just now, that there was an influence of the cervicire on mortality. So a bit better model would be to look at litter survival and then the same herd year season, correct for the cervicire, and then look at genetic differences between the sows. An improved situation would be, and that's why it's underlined, to add the pedigree to cervicire and add the pedigree to the sow, so that you can find the genetically best boars. So select in the boars, in the sire lines, and select in the dams for the genetic improvement. What I personally think is best to not look at the parity level, at sow level, but to look at individual piglet level. So the unit of observation is a single piglet. You look in your barn, you weigh your piglet, have your, herd year seasonal things, and then survival is a function of birth weight, the S curves. So if a piglet of 500 grams, if it lives, it must have good genes, that type of idea. So we correct for this livability, and then estimate the effects of animal, the piglet itself, the genes of the piglet, including that is cervicire plus dam. And then we look at dam, and livability for me is including the stillborns. So if a piglet is stillborn, it could be that it is big and short, and the dam influence is if the dam is too narrow. There could be two reasons why a piglet is stillborn. It could be the piglet, or it could be the dam. Similarly, if a piglet dies during lactation, it could be the genes of the piglet, or it could be the genes of the dam. If the dam doesn't produce milk, or she is active, or whatever. So it's the foster, and very often dam and foster are the same, because cross-fostering is only 10%, or sometimes it's 100%. If you chase all the piglets in the driveway and then redistribute them, then it's 100%. But generally it seems to be around 10%. Except in the Scandinavian countries. There are some colleagues from Norway here. What's the average farm size in Norway? 53 sows. Well, maybe it increased to 80. In that situation, you don't have cross-fostering. So in reading the literature, every now and then I have a bit of problems. Then it's, why is cross-fostering not mentioned? Because it was not possible. Okay, so animal effect for me is piglet vitality. How strong is the piglet? And the foster effect is mothering the ability. There's the piglet weighing protocol in which each and every piglet is weighed. Oops. At the rate of 500,000 piglets per year. If you do that, then you can run the analysis which I showed you, and you have the average the birth weight of piglets, and you have the litter weight of the sows, and you have the uniformity in birth weight, and you have the number of the underlines. So it is the big investment, but it helps in the analyses to come. So what we do is we put all these data through the breeding value estimation, and then you can find litters 100% in this situation. There is 100 litters with a low breeding value for survival, So it's gestating sows, and you have the breeding value of the sow and the breeding value of the service sire, 100 low and 100 high. And then you get the differences like this. The expected survival on the basis of breeding value was 4%, and then the realized was 3.1%. So it does work. We tested it time and again. It does work. If you estimate the breeding values for survival and you apply it, you get what you want. Then what farmers tell me, yeah, hello, this is easy. Because you'll get the smaller litters, the high the survival families will have heavy piglets and quite few. So these will be the 8 piglet litters, and these will be the 16 piglet litters or whatever. But that is not true. There is no genetic correlation between litter size and genetics of survival. And in terms of birth weight, what you get is the opposite of what you expect. If you select for the survival, then you get lower birth weight. And I'll explain you why that is. And your variation in birth weight goes down. And that was our original second option. Reduced variation makes piglets stronger. Now enter the piglet vitality, the piglet, and after that I will have a look at mothering ability and see what mothering ability can add to this system. So this is the animal effect from the model. I try to show you that it works. If you take on EBV, then you see that it works, but why does it work? So what we did is we took 25 high EBV gilts, and really from a multiplication the barn we waited for 3 months and picked the very high EBVs out, and we picked the 25 very low EBV gilts out, and we mated them to the best and the lowest which we could find in our country, because we have access to all these AI studs. And all these 50 the gilts were Caesarean, how do you call it in English? Sectioned? Caesarean sectioned? Okay. 2 days before farrowing, and we weighed all the placenta, and all these the 650 or something the piglets were fully dissected. We really took them apart. So we took the weights of the organs, the length of the intestinal tract, we took blood and whatever. And what came out is that the more vital piglets had heavier livers, and they had more glycogen in the body, and then at a p-value of 0.04, which was kind of a bit disappointing, because we took, 122 different traits, and then only a few were somewhat significant. I'll come back to that. We have the placentas and the individual birth weights, and then they're linked. So this is this tagging system. You get a piglet, and then you tag the umbilical cord, so that later on you can find which placenta fitted the specific piglet. So in general, there is a clearly positive trend. If you have a larger placenta, then you have a heavier the piglet. Blue are the high EBV litters. I draw 2 lines, and if you look to the right of this line, the majority of the dots is red. Actually, almost all the dots are red. So if you select for survival, you lose the very big placentas. On the low side, it appears that the blues and the reds are, well, more or less in agreement. So selection for litter size, you lose the heavy the placentas, but you don't gain or you don't lose the extra small ones. Similarly, if you look above this 1600, it's almost all red. You lose the large piglets. You lose the large placentas and you lose the large piglets. So selection for survival reduces birth weight because you don't have the excessively heavy piglets. In that sense, you gain uniformity. And because you gain uniformity, gestation length increases, and the piglets are born more mature, more at term. The high EBV litters have more cortisol. Well, I explained you that we checked almost everything which we could think of. So there's hematocrit, there is glucose, the venous glucose, arterial glucose, there is for some reason serum estradiol. and there was a serum cortisol. And this is litter average and the p-value. And so it's the slope on EBV. So the piglets with more EBV for survival, the stronger piglets, they have incredibly significant more cortisol. If you look at the role of cortisol pre-farrowing, because everybody knows cortisol as a stress hormone, but if you look at the cortisol pre-farrowing, then it helps to maturate the lungs. It finishes the lungs. So if you don't have the cortisol, enough cortisol, then the lungs are somewhat inadequate. So then you're born with inadequate lungs, and the first thing you need is the oxygen to start to get around. The second role of cortisol pre-farrowing is the production of glycogen. Once you're born, you need to breathe, and the second is you need to reach the other. So if you have more glycogen, it helps. And then if you relate back the piglets, they had significantly 0.04 more glycogen, and they had heavier livers. And the heavier livers were because of the extra glycogen. If you take the glycogen out, then the livers had the same weight. So it all makes sense. Selection for the piglet survival works, and it works through this maturation at the end of the gestation. So what you end up is two survival curves. That was my option 3 in the beginning. So at 1 kilogram there is quite a bit of difference. So the high, the blues, the high survival has a higher curve. And what you can see that the high survival families lack the very heavy piglets. The very heavy, the 2.53 the kilogram piglets which we used to see, they are not there anymore. So it's more uniform, but a bit lower average. Then go to mothering ability, the Foster effect in the model. What we like in a sow are things like this, I guess. They're quiet, attentive, enough teats, quality of teats, enough milk, uniformity at birth and uniformity at weaning. And maintenance of body condition, that they don't lose too much so that they can rapidly start a new parity. So in a selection the program, if you realize this, then you can start measuring all these traits. But you need a lot of grad students, I'm afraid. Second option could be to believe my statistical model and say, okay, if we have these breeding values for mothering ability, maybe those will take care of this long list of traits we're interested in. So we did quite some trials, and I'll show you the results of a behavioral trial. And the behavioral trial, kind of had 4 different chapters, and one of the trials was visual scan sampling. It meant that, I started out having students who sat behind the sow and looked at the whole farrowing process. And then in 3 or 6 months' time, they would have 30 observations. On the basis of 30 observations, it's very difficult to estimate the heritability. You need at least 40, I guess. So I wanted to have a student who could do more. And in this situation, what she did, she walked for 4 hours or something through the farrowing rooms and at walking speed or something. And then the first pen, she looked at the sow and said, okay, what is the position and what's the behavior of the sow? And then the left and right, and then the next farrowing room, and then return to the first one and do the same scoring again. So then she could do 30 sows on a morning, and then there are different observation days, and in the end she did 80 sows and a lot of traits. In terms of the position, the sow could stand, she could sit, and she could lie down, or she could offer herself to the piglets. But this is position, and the results will come back. In terms of behavior, she could be suckling the piglets, she could be exploring, and she could be paying attention to her piglets, socializing, she could check the environment, and that will come back to. The second one was open the field test. Literally, we dropped a red bucket from quite high, and then looked at the reaction of the sows. Then we did an aggression test pre-farrowing. There were no piglets. Then we provided this push piglet with the batteries inside, and it could jump and make noises, and looked at behavior of the sow against these. And we had a questionnaire. And the questionnaire was about aggressiveness to people, aggressive to piglets. So it was filled in for an individual sow. No care for piglets, fearful during handling. You could record the number of the teats. You could record the regularity of the udder. And you could look at litter quality at birth. And this is the average weight, so relatively heavy piglets. And normal the variation. And relatively normal weight at 3 weeks. And at the same time we looked at variation. So a little variation here and normal variation on this side. Okay. Scan sampling, the sows with a high breeding value for mothering ability had less changes of posture. So once they were lying down, they stayed lying down. They had less activity, and they were less in sitting position. I'm a quantitative geneticist, so I know very little about the behavior, but sitting is a wrong sign of sow. If a sow sits, then she's nervous. Sows with a high breeding value for mothering ability had more exploring behavior in the open field. So that bucket that came down, and then, of course the sow, not even each sow, but most sows, it's like, And the sow with good mothering behavior very quickly go to the bucket and see what happened. So it is the exploring behavior. In the aggression test, we found out that the good sows were more laying on their side, offering themselves to the piglets, pre-farrowing. Pre-farrowing. They had more vocalization, and it's not that loudness, but trying to speak. To that push piglet, trying to communicate, to figure out what is wrong. And they had less aggression. We lost one of the push piglets because, we didn't, the sow ate it, including the battery. In the questionnaire, there is all these traits, and then there is the heritabilities. And if you could focus on this column, the red column, the genetic correlation of my estimate of mothering ability, it's strongly negative with aggression and fear traits. There is little relation with weight at birth and weight at weaning, but there is a strong positive correlation with uniformity at birth and uniformity at weaning, which is good. The good mothers have more uniformity as scored by the farmers. Regularity of the udder, it was slightly positive, and number of teats, that was 0.4. That's a good genetic the correlation. So my conclusion from this is that the statistical model results in what we want. You get quiet sows, you get attentive sows, you get more teats, you get more regular udder, and you get more uniformity at birth and at weaning. So instead of grad students, we could use this breeding value. How to implement this in a breeding the program? Oops. This is a table which comes out of the breeding value. Every weekend or something we run these reproduction the traits. And then here it says farrowing survival on an individual piglet basis and pre-weaning survival. So there are by now 4 million piglets which have been weighed, and then the farrowing survival based on these 4 million the piglets is 92.94%. And that is across all lines, all crosses worldwide over the past 10 years or something. Then the stillborns can't live until weaning. So the number of observations for the pre-weaning survival is lower because this difference is the stillborns. And then there is an average of 89.44%. So give or take, there is a 10% mortality here and there is an 8% mortality here, which relates to the original 18% of losses. The one piglet stillborn and the two piglets pre-weaning the losses. We have scores of the underlines on 2 million piglets. Heritability of the number of teats is 0.38 or something. So we have very accurate breeding values for number of teats. In given time I can tell you a small story on that. Longevity, there is longevity estimates based on the 1.2 million sows. And then total borns is 6 million records, which makes sense because each the sow has on average 4 or 5 parities in the database. It's a repeated measurements. And if you look here, then this is stillborn on sow level, sow level, and this is stillborn on a piglet level. We don't have protocols on all farms, these detailed protocols, but on quite a few farms. We have even more data of stillborns on all farms. So everything is put into a huge database and estimated into breeding values. Does it work on a large scale? So there is a new validation step. And this is what we tend to do for lots and lots of trades. Take these whatever million data set and then take out 10,000 records or 100,000 records, it doesn't matter. And then estimate the breeding values on the remaining data. And if your pedigree structure is in order, then you have breeding values of these 10,000 animals. And you have the phenotypic observation because you took them out of the data set. So then you can look at the correlation. So you predict what these 10,000 should do, and then you expect a B value, 1 unit breeding value for litter size. So if a sow has a breeding value of 0.3, then I expect that on average her performance will be 0.3 piglets. If not, then there is something wrong. Okay. So number total born, the B value is 1.09. So we get a bit more piglets than we anticipate on the basis of breeding values. For average litter birth weight, it's 0.99, litter variation 0.88, and gestation length is 1.02. Survival, that is including the 3 animal effects. So it's the animal effect and the dam effect, and it is the foster effect. If you combine all of that, then you get the 0.73. So there is still a bit of work to be done to really tweak the whole system so that we get the very best results. But 0.73 is very good already. I'll lower my voice. Oh, Max is here. Genomics helps for traits late in life. They're the traits which are sex limited and traits which have a low heritability. So if this is your normal system, well, actually this is accuracies, and then this is what you could realize with some use of the genomics, and then this is the gain. So for the trait daily gain, and I only looked at the sire path here. I ignored the dam path. So that you have the sex limited situation. Then for daily gain, the use of genomics and the full genomics is 15%. For feed intake it's 16%. For backfed it is 14%. For total number born, it is more than 100%. If you select a boar piglet right after it's born, it doesn't have an own performance, And if you select it at 7 months of age, it doesn't have no performance. If you select it at the age of a year, then the sisters will have a performance, but that boar will still not have the performance. Only after it has its own daughters, the dairy cattle situation, and milk production in dairy cattle. It takes a long time before you really start to understand whether or not this boar is a good boar. So the value of the genomics for traits like total number born, stillborn piglets, mothering ability, litter variation, stayability, it's all huge. And then surprisingly, well, not surprisingly, but for the number of teats, it's only 10%. But teats is part of the mothering ability, yeah, but it has a high heritability. The number of teats, you can count the number of teats in a pig, and you can count the number of teats way before you want to select it. At the very moment that the piglet is born, you can do the selection already. Something similar is for piglet survival. There's lots of information at the moment that the piglet is born. If it survives itself, or the brothers and sisters survive. So, general conclusions. Survival has to do, it has to do with management, and it has to do with selection. If you don't do a thing about management, then we need to select for many centuries in order to make piglets that strong that they can survive anything. But so that's not the idea. Survival selection is hard work. We have to collect lots and lots of data, but it's very feasible. There is lots of genetic variation which you can exploit. Most genetic companies select for survival, be it with different tools. Some do it on a litter level, some do it on day 5, some do it with the genomics, and some do it with extensive data recording. Faster than economic progress should be an option. Okay. We increase litter size, and with litter size you increase the efficiency. So you can stick the economic values in your model and then select for the mortality. And the simulations show that mortality will still increase a bit, but you get more weaned. So we allow ourselves to get more the mortality. So my should indicates that I would like to weigh mortality more than economic, and in that way maintain mortality at the same level, or preferably even reduce mortality. You'll get things like longer gestation, lower variation in birth weight, but not higher birth weight. So my original the slide of of 12 weaned in 10 years time, I would like to raise that to 13 and a half. The goal that a good farmer should have. Reduce the number of ova shed. And I don't know how yet, but not overcompensate the whole system. Make it a robust, normal system. Maintain the 15 piglets born and half the mortality in terms of stillborn, of pre-weaning mortality, of nursery mortality, and of finishing mortality, so that in 10 years time, instead of 76% for a good farm, we could send 88% of the total borns to market. In terms of genetic trends, what we observe is the normal, everybody can show a slide like this. It is the normal trend for litter size. This green line is mortality, and this blue line is the number of teats. And there is a clear break, and if the chairman allows me during the discussion, I might go into that. So my plea for today is to try, all of us, to get to the green line, reduce mortality, and at the same time maintain the progress in litter size.